Okay, beta decay is a little more complicated than alpha decay. We actually have three different types of beta decay, and we'll look at these in three separate videos. So our three different types are beta minus, and we'll draw that with a symbol with beta, the letter beta, the Greek letter beta with a negative, beta plus, and then we have electron capture. And the symbol we'll use for that is just going to be EC, the abbreviation for electron capture. Let's look first at beta minus decay. So in beta minus decay, we have a neutron that becomes a proton, that's a P, plus a beta minus, which is going to be effectively an electron. So it has a charge of -1 plus a neutrino. This sort of looks like a V. It's the Greek letter nu, so it has these sort of slanty sides. In this decay, a neutron splits into a proton and a beta minus particle. So a neutron, that's this thing, splits into a proton, that's this, and a beta minus particle. The beta minus particle is the same as an electron. And you can see that if a neutron that has a positive charge, a neutral charge, no charge at all, if it splits into a proton, then it has to also split into an electron. N is the neutron, P is a proton, this particle with 0 and -1 is the beta negative particle, and the neutrino, or actually this is an anti-neutrino, has no charge at all. And that's really what you need to know about the neutrino. It has no charge, it's neutral, and it's also really small. That's why we have the Eno. We'll see that in just a bit. So neutrinos have no charge. That means they're neutral. And they have very little mass. Their mass is basically 0. It's a little bit above 0, but it's basically 0. And they move at very, very high speeds. I'll show you a video later, but it's important, the neutrinos, because it allows for conservation of energy and momentum. They take energy away from the particle. An antineutrino is anti just because of its spin. So that we get this part, the antineutrino, because of its spin. As I said, we'll watch a video about this in a bit. Don't sweat that too much about the spin of the neutrino. It's not terribly important for what we're talking about. It has no charge, just like the neutrino. It's neutral. And it has very little mass. It also travels at very high speed. So it's neutral, and then this Eno, which means small, like a gambino, right? I don't know. It's Italian, I think, but it means that it's really small. And they help to account, these neutrinos, for lost momentum and energy. We'll watch this video. I'll put it in the notes for the screencast. But what is a neutrino? Let's do an example of a beta minus decay. Let's say I have a carbon 14 and it's going to beta minus decay where it emits a beta minus particle and a anti-neutrino. Well, let's see. So I have this carbon-14. It's going to emit some particle. We'll come back and predict what that's going to be, plus my beta minus particle. That's that, plus an anti-neutrino. And so what can it be? Well, I have to do my conservation. I know it's going to be a 14 up here. Oops. And then this has to be 7. So what is my 7th element on the periodic table? You can take a look. It's in the back of your book, by the way. That's going to be there. So let's do. All right, so that is my nitrogen for the beta minus decay. And then I can look at my rules. So I have 14 is equal to 14 plus 0 plus 0. So this neutrino has 0 mass as well. And then as far as my number of protons, I have 6 equals 7 plus my -1. So looking at this for my my beta minus particle.